Thank you everyone for being here, and thank you for the opportunity. My name is Mashaal Musleh. I am a PhD candidate at University of Minnesota, and my research interest focuses on improving the quality of map services like routing, navigation, and all these kinds of stuff. It's my pleasure today to share with you one of the tools that we needed during our research, so therefore we built it. And today I'll be sharing with you, so the community, hopefully the community can use it and build on top of it. So the tool is named RASED, and it's a scalable dashboard for monitoring road network updates in OSM. I'll get into the details in a minute, but let me quickly give you the outline that we will talk about. I'll start with the motivation and what are the queries supported by RASED, and then what is the architecture for RASED, and then quick experimental results, and then I'll show you a quick demo for RASED in action. So starting with the motivation, I guess you guys all here, like you know OSM, so I don't need to convince you how important it is OSM, but in other situations, like I have to convince people how important it is the map and OSM, because it power plenty of applications. And because of this importance, there are a lot of researchers that try to analyze the map, try to analyze OSM in order for to have like a quality assessments and so on. However, all of those analysis and studies usually focus in local regions, like it's not global. Usually it's like limited by specific region. And why is that? Because OSM, as we all know, has huge amount of data. So for example, if you look at the full history of changes since the beginning of OSM until now, there are more than 12 billion updates in the map. And if you look at the full data file uncompressed, it's more than 3 terabytes of data. So that makes it for researchers who want to study all this amount of data is like very difficult, and they like have very deep technical skills to process such amount of huge data. In a nutshell, existing surveys and studies for analyzing the data in OSM is not scalable. It's always limited to a certain area. So here comes RASED. It aims to provide a global scale and comprehensive and highly interactive analysis for the data in OSM. So therefore, like researchers can use it. What kind of analysis and how does RASED help map analyzer in this case? So the use case that we needed, we wanted to see how often the roads are changing in OSM, globally and in the US. So the reason we needed such a question, because we were working on trying to convince people that we need to work on the map, and they said, no, it's stable, there is no much of changes. The road and the map in the US is almost stable. So we needed to show them how often the road is being updated. So that could be like new addings to the map, or updates to existing roads, not only like their topological data, but also including their metadata. So the road can stay, without change, but you add new metadata about speed, about restriction and the direction and so on. So the goal here is to show the number of updates with statistics. So we can see how often it changes, the map is changing, with various query scenarios that allow you to compare countries, to focus on certain type of roads or certain areas, either like large period of time or small period of time. So there's like numerous query scenarios. And RASED supports like all the history of OSM data. So it's almost 16 years worth of data. And all of that is scalable and interactive dashboard. And when I say interactive dashboard, I mean each query that we'll see examples of them just in milliseconds. So that's a quick motivation. Let me show you an example of RASED analysis queries. But first of all, I want you to imagine that we want to have such a table. So this is just an imaginary table. There is no table like this in OSM. So we're going to imagine constructing. We call it example update list. So think of the column. We have a date of something changed in OSM, the country, the road type, like service, residential roads, and so on, and the element type in OSM, way, node stats, etc. And the type of update, whether it's a new or a topological update on the road, or is it like just a metadata or tags update, and then the precise location and the change set ID. So the goal, the queries is like you can have any aggregation on those columns highlighted by the red rectangle. So 5 columns. So and then you have aggregation on those columns, and then you have filters on them as well. So let's say give me only on USA, or like a period ranging from 2021 to right now, for example, or only service road, or service and residential. So any filters you want on those columns, any aggregation on those columns. And the goal, find the number of updates in OSM and their percentage, like per country or comparison between them and so on. Quick example. Maybe a quick show of hand, how many of you guys know SQL query, so query databases? Okay, if you know SQL, maybe you can understand this, but if you don't know SQL, don't worry about it. We are not using SQL. It's just like illustration, what are the queries? So look at the textual example, like find the number of newly created or modified nodes ways relation for each country, and for each country road report in 2021. And RASED will give you this visualization, so you can see the top countries and the number of updates and so on. So to get this visualization result, believe me, it's not easy, especially when you know the amount of data that I just showed before. If you have a relational database and you run this SQL, it will take a long time to answer this query. So that's an example. So RASED queries are always supported in order of milliseconds to enable interactive visualization and interactive dashboard. Another example, compare the percentage of daily changes in road network between Germany, Singapore, and Qatar. A third example, find the number of newly created or modified element types, and so on. So these are all examples of the queries that we aim to answer. So how does RASED do this? So it has 4 main components. Data collection and processing that takes daily data from OSM, and then second and third component, storage and indexing and query execution, which are the main, the key components in the system. And finally, the user interface we'll see it in quick demo. So first of all, the data collection. So we get the Planet OSM file. There are a bunch of contributors uploading to it every day. So we get every day the diff data. And I think most of us are familiar with those data. So we get the daily diff, we get the change sets every day. And then, so from those, we can construct those columns from the table. So we get the date and country of what type, element type, that one of change set ID. For those who doesn't know the diff data, it's like a daily file prepared by OSM that shows the elements that have been updated compared to the day before. So we collect that every day. And then we have one more column that we need to access to. So if we want to know the previous version to the element of OSM without issuing queries, so we get the full history every while. So in our case, we run it every month. We call it the monthly crawler, so we can compare the different versions of it. So we have this update list U, and then next we want to this table is created every day. So we keep appending this table. At the end of the day, it's going to be a huge table. So that's the need for the storage and indexing. The goal of this module is when you have a query, you send it to this module, and this module reads the data from daily updated list in certain way, such that it just generates very few I/O. And for those of us who have dealt with databases, the less I/O you have, the faster the query you have. So, the faster the query results. So it's very important to have as minimal number of I/Os as possible. So how we do that? We construct a hierarchical temporal index that is shown in this picture. I'll explain this index quickly. So the nodes in the index are data cubes, and what are those data cubes? Are basically aggregations for the number of updates. So we have a 4-dimensional data cube. We have around 300 country, 150 road types, 4 updates type, and 3 element types. So the value on each cell in the cube is basically the number of updates in OSM corresponding to those elements. Think of it like if it is a 2-dimensional table, so you have say country and dates, then imagine it's a 3-dimensional cube and then 4-dimensional cube. So each cube has more than 500,000 pre-computed values, and it's around 4 megabytes on disk. And those for who knows databases, it's very important that each data item always fit in one page. So the way these numbers are designed so that each cube can fit in one disk page. And then we have 4 levels of these cubes. One of them one of the levels are for daily cubes. Then we have a replicated level of weekly cubes, and then monthly cubes and yearly cubes. Just a quick stats. So in total, we have 7,000 nodes, 4 billion aggregated values. The whole index roughly about 28 gigabytes. And then to maintain this index, we have a daily updates that are being added to it. There is no update. There is no update to previous values because these are corresponding to changes to OSM. So if a change has happened, you don't need to recount it. It's already there. So that's the maintenance of the index. Third component is the query execution. Okay, so we have a query now, like find the number of updates in each country and time window. So the query goes in 2 phases. First of all, retrieve the cubes that satisfy the time period. And this is a disk-based, you retrieve it from disk. And then slice the cube to get the dimension that you are interested in. And this is in memory. So the main bottleneck is in the disk-based one. So we need to optimize it. So we do 2 levels of optimization. One is caching, and second is level optimization. Caching is the main idea is, okay, let's keep the cubes that are frequently asked in memory, so you don't have to go to disk and bring them back, because it's always costly to go to the disk and bring them back. So keep them in memory. So that's caching. The rationale is the more recent days or periods, the more frequent, the higher the probability that you want to ask about them. So keep the most recent cubes. Of course, you can control like the resolution between the 4 levels, which cubes daily, weekly, monthly, and yearly to keep in memory. For the level optimization, again, since that we have the query, find the number of updates during the period from January 1 to February 15, that's 46 days. So if you have these cubes daily, weekly, monthly, so there are 3 possible ways to answer the query, either read all the daily cubes, or read 6 weekly cubes and then 4 daily ones and aggregate them, or 1 monthly cube, 1 weekly cube, and 8 daily. So the cost is in the number of cubes retrieved from the disk. So here we see 46, 10, 10. And an optimizer will choose 10 cubes. However, this optimizer is cache aware. So remember, we said like we have some of the cubes in the memory, so we have to take into consideration what cubes are in memory. So if assume we all have all the daily or the most recent cubes, daily cubes in memory, so the cost for all daily will become 0 disk IOs because all are in memory. So that's what give you the best answer. User interface is basically what takes the input parameter and shows you like various visualization, either tabular, charts, and so on. I think I'll show you a quick demo, and I will skip the experimental results in favor of like letting you see the actual page. So I have so the RASED is available online. You can access it at rased.cs.umn.edu. And I'll play the video. It's a recorded video, but it's available online the same way. So you start by defining the time of interest that you want to see the number of changes for. So here, I guess from 2020 until 2021, so almost a year. Select what type of roads you're interested in, and then hit query data. As you can see, so each interaction you will see now is basically a query going to the data, and so all of them are a few milliseconds. So here are the number of updates per country. As always, like you can see, the US almost 19 million updates during this period. You can see them, you can filter them in areas, locations, US, and other parts of the world. You can see all the list of the number of updates or visualize them as a chart. Yeah, like you see, like you can see how many ways have been created, have been modified, relation nodes, and so on. You can see for US, you can see like per state, or use this as kind of intuitive time lapse to see how updates are happening in the US across the period that is defined. A third visualization can be seen now. Okay. Yeah, if you select a certain country, then you can see the updates for that particular country. Here, like we see the roads type. So service roads are among the top ones being changed or updated frequently in the US. They make sense because highways are almost like it's there for a while, so they are not updated, but maybe services and residential roads are being created or being added to the map. fourth view shows you quick time series chart to see how things are changing across the time. For the sake of giving you time to have questions, yeah, you can see individual updates like based on the filters that you have. You can see like sample of those updates, and it will take you a link to Overpass to see the exact update that matches your query filters. Yeah, you can also do the same for tags or metadata. We call it metadata like max speed and so on. And yeah, with that, I conclude and thank you so much.